Okay, so the endocrine system is an internal regulatory system similar to the regulatory actions of the nervous system. The endocrine system is going to help us maintain our internal environment by helping us stay in a homeostatic range. And the effects of the endocrine system are wide ranging. So it'll help us regulate metabolism, regulate our growth and development. It regulates our sexual function and our ability to reproduce. It regulates our sleep with our circadian rhythm. It impacts our mood. I could go on and on. So the endocrine system is incredibly important to our health, and it influences this metabolic activity by means of hormones. So hormones are like little chemical messengers that are secreted by cells into the extracellular fluid. More often than not, that's referring to the blood. And these messengers will travel through the bloodstream to distant body cells to signal a specific physiological response in those cells. So the whole reason why we call the endocrine system a regulatory system is because through these hormonal signals, the endocrine system controls and integrates the functions of other body systems. So for example, we see the endocrine system, specifically the pituitary gland, controlling almost all of the signals for our reproductive system. So every month in women of reproductive age, her body prepares an egg for ovulation. And the lining of her uterus will build up to make a nice little nest for this egg, and that is all controlled by follicle stimulating hormone and luteinizing hormone. Gentlemen, have no fear, you have FSH and LH2, and in men, it stimulates the production of sperm and testosterone. So through these hormonal signals, the endocrine system is able to control and integrate the functions of other organ systems. I really enjoy the endocrine system because it's so complex and there's so many moving parts, but it really illustrates for us how everything is connected. And in modern medicine, we have this tendency to divide the body up and have a specific doctor for each body system. But the endocrine system reveals a flaw in that system because the body systems are not separate from one another. They are all interwoven and connected. And so it's imperative that we don't lose sight of that whole body approach. So the organs, the organs containing endocrine cells can be divided up into primary endocrine organs and secondary endocrine organs. That is pretty straightforward, so let's just read the definition here. Primary endocrine organs produce and secrete hormones as their primary physiological role, whereas secondary endocrine organs produce and secrete hormones in addition to their main function. So with a primary endocrine organ, their whole purpose in life serves an endocrine role. So examples of primary endocrine organs are the things like the pituitary gland, the thyroid gland, the adrenal glands. A secondary endocrine organ, on the other hand, will be an organ that essentially has its own thing going on, but then in addition to its real job, it has a side gig with endocrine functions. An example would be something like the kidney. So clearly the kidney's main job is filtering the blood to make urine, but in addition to that, the kidneys also produce a hormone called erythropoietin, which we talked about in the blood chapter, with EPO stimulating the production of red blood cells in the bone marrow. Another example with a secondary endocrine function is the skin. So the skin's main function is protection, right? Forming this external barrier to cushion and insulate the deeper body organs. But its side hustle with the endocrine system works to synthesize vitamin D. So when UV light hits our skin, that starts the process to synthesize vitamin D. And don't let its name confuse you. Vitamin D, though we call it a vitamin, it's actually a hormone. And vitamin D is vastly critical to our health. I will spare you my drawn out spiel for now, but it's a critical nutrient for us because it supports the health of our brain, our immune system, our cardiovascular system. It helps regulate insulin, which helps us stabilize blood sugar levels, so that could modulate the effects of diabetes and obesity. It is linked to our mood and or depression with dopamine production and serotonin levels. It plays a significant role in female fertility, And all that to say, roughly half of the US population is vitamin D deficient. So that is rather concerning for the health of our overall population. But nonetheless, the skin is a secondary endocrine organ because of its side hustle with a variety of hormones. Okay, so we talked about how hormones are like little chemical messenger molecules, and they travel through the bloodstream to their destination location to signal a characteristic physiological response. So, unlike nerve impulses, which fire and act very rapidly, hormones travel slowly through the bloodstream, so they'll float along until they reach their target tissue. So the endocrine system regulates more slow processes, but its actions have widespread effects. Since hormones are secreted into the bloodstream, an important characteristic we need to consider is its solubility in water. And this matters because we can't have hormones coming out of solution before they get to wherever they need to go to. So there are two broad molecular categories of hormones that we'll talk about, with it either being amino acid-based or steroid-based molecules. The amino acid-based hormones are our amines, our peptides, our proteins. So think back to cellular physiology. These molecules are typically water soluble with the exception of thyroid hormone. So because they're water soluble, they cannot easily cross the plasma membrane, which is important because it affects how these hormones are able to bind on their target cells. So we'll see the receptors for water-soluble hormones located on the surface of the cell, so the hormone doesn't have to deal with trying to find a transporter protein to get inside. On the other hand, these steroid-based hormones are lipid-soluble, so they can diffuse across the sea of fatty acid tails of the plasma membrane with relative ease. So their receptors are going to be located on the inside of the cell. Let me repeat that just in a more simplified way. So receptors for water-soluble hormones must be located on the surface of the cell, so within the plasma membrane, since these hormones cannot enter the cell. The receptors for lipid-soluble hormones, so our steroid hormones and our thyroid hormones, are going to be located on the inside of the cell because these hormones can enter the cell. All right, so let's get started with some actual glands and hormones then. So the first gland we're going to talk about is the pituitary gland. And you've probably heard this referred to as the master gland of the body before, and that's because it secretes several major hormones. The pituitary gland is very small, about the size of a pea, and its shape kind of resembles a golf club, with the gland itself forming the head of the club, which we can see here, and then the stalk of the pituitary called the infundibulum, forming the shaft of the club. So the infundibulum is important because it connects the pituitary gland to the hypothalamus, which we'll see the significance of that throughout these next few slides, because the hypothalamus controls the release of hormones from the pituitary gland, but in two different ways. So you've probably noticed that the pituitary gland has two major lobes, the anterior lobe of the pituitary and then the posterior lobe of the pituitary. And the hypothalamus interacts with both the anterior and the posterior, but in different ways. So let's talk about the anterior pituitary first then. So the hypothalamus interacts with the anterior pituitary gland primarily through the hypophyseal portal system. And the hypophyseal portal system is just a capillary system. So teeny tiny blood vessels that flow between the hypothalamus and the anterior pituitary. And the hypothalamus will secrete hormones into this portal system, and they will signal for the pituitary gland to produce and secrete its own hormones. So what happens is, when appropriately stimulated, the hypothalamus will secrete either these releasing or inhibiting hormones into those special blood vessels, and those will travel through the portal veins to the anterior pituitary, where they will tell the anterior pituitary to either release or inhibit the release of its own hormones. So we can see some examples in this table here with gonadotropin releasing hormone coming from the hypothalamus to stimulate the anterior pituitary to make and secrete FSH and LH. So you don't need to memorize these specific hypothalamic hormones listed in this table. I would just keep a general understanding that releasing and inhibiting hormones from the hypothalamus control the production and secretion from the anterior pituitary. An important characteristic to point out is that hormones of the anterior pituitary are made in the anterior pituitary. So the anterior pituitary synthesizes its own hormones, and we'll see that in contrast with the posterior pituitary, who does not make its own hormones. We have 6 major anterior pituitary hormones described in this table. So in contrast to the hypothalamic releasing and inhibiting hormones, which you do not need to know, you do need to know all of these hormones listed here. They are pretty straightforward, with thyroid stimulating hormone stimulating the thyroid to secrete thyroid hormones T3 and T4, growth hormone stimulating obviously growth. We have FSH and LH, which we've already talked about. So the mnemonic flat peg, which I have over here, flat peg is useful in learning and memorizing these. So F for FSH, L for LH, A for ACTH or adrenal corticotropic hormone. And by its name, we know that it's going to stimulate the adrenal gland, specifically the cortex, with adrenal cortex, adrenal corticotropic hormone. P, we have prolactin to stimulate milk production. G, we have growth hormone, but what about E? So E stands for endorphins, which we don't cover in this class, but if you're curious, their role is in pain management. So they're like natural opiates, our own form of morphine, so to speak. So they reduce our perception of pain under stressful conditions. Again, we aren't going to focus on endorphins in the lab though, because it just gets more complicated with the nervous system. So you can think E for endorphins or E for extra, just like your free space in bingo or your extra letter in my mnemonic. So with the posterior pituitary, the posterior pituitary is different from the anterior pituitary in that the hypothalamus is going to make or synthesize these hormones and just deliver them to the posterior pituitary to be stored and then released when needed. So with the posterior pituitary, we have hypothalamic hypophyseal tract running through the infundibulum, connecting the hypothalamus to the posterior pituitary by way of these long nerve fibers. So we can see these here, these long axon terminals running all the way down. So what happens is the hypothalamus will synthesize both oxytocin and ADH, and then oxytocin and ADH are transported down the axons of the hypothalamic hypophyseal tract to the posterior pituitary, where they are stored in axon terminals. So the hypothalamus basically just delivers these like a little package to the posterior pituitary. So whenever the associated hypothalamic neurons fire, the axon potential propagated down the axon terminals will cause the hormones to be released into the blood. So I've said it a few times now, but the distinction is really important. The anterior pituitary will receive signals from the hypothalamus via these releasing and inhibiting hormones that cause the anterior pituitary to synthesize and secrete its hormones. So the anterior synthesizes its own hormones, and then with the posterior pituitary, the hypothalamus synthesizes those hormones, so the posterior pituitary does not make any. It's just a storage site until it's time to be released. A fun thing to point out are these other scientific names for the anterior and posterior pituitary, and it may actually help you remember the relation to the hypothalamus. So with the anterior pituitary then, it can also be referred to as the adenohypophysis. And so that suffix there, adeno or adeno, has a Greek origin referring to gland. So the anterior pituitary has this glandular tissue, which you can see on the histology slide at the very end of the PowerPoint. The anterior is very dense with this glandular tissue, which makes sense because the anterior is the one that has to manufacture and make all of its own hormones, like a true endocrine gland. And then with the posterior pituitary, we can see that also referred to as the neurohypophysis. So neuro, obviously referring to nerves. That's pretty easy for us to see that connection there with the hypothalamic neurons, making these hormones and passing them along the nerve fibers to be stored in axon terminals. So to just briefly touch on these hormones of the posterior pituitary, ADH, or antidiuretic hormone, also called vasopressin, I'm hoping you remember this from the renal lecture. We know that vasopressin is going to act on the kidneys, specifically the distal convoluted tubule and the collecting duct, to help us retain water. So we will produce less urine, so anti-diuretic or against diuresis. So if you aren't aware, diuresis is a clinical term that we use for excessive urination. So if we give someone a diuretic, we are encouraging urination. If we give them an anti-diuretic, we would be discouraging urination. Oxytocin, you have probably heard called the cuddle hormone or the love hormone. So physiologically, we'll see its most notable role in childbirth, enhancing that motherly bond, but we can also feel the effects of oxytocin in other social relationships, often romantic relationships that have a strong feeling of connection and trust. So it's just like that delicious moment, that feel-good bonded connection that you have with your partner. Fun fact, estrogen promotes the release of oxytocin, whereas testosterone blocks the release of oxytocin. So men and women do not secrete the same levels of this hormone, and that may be a physiological basis behind the stereotypical lovey-dovey, let's just cuddle on the couch feeling from a woman, and then the like not as intense feeling or desire for lovey-dovey stuff from a man. The pineal gland has some really interesting history associated with it. It's a bit of a mysterious gland, so I find it to be really intriguing. So the word pineal actually comes from the Latin word for pine cone. So it got its name just because of how it looks. It kind of is shaped like an itty bitty pine cone. And in the 17th century, a French philosopher named Descartes was particularly interested in anatomy and physiology, and he had much to say about the pineal gland. He referred to as the pineal gland as the seat of the soul, and it is related to the third eye for spiritual reasons, but also biological reasons because of its location deep in the center of the brain, and also because of its connection to light. So the pineal gland secretes only one hormone, and that is called melatonin. You've likely heard of melatonin before. It's just the hormone that makes us feel sleepy. And this regulates our circadian rhythm, which is just our natural internal process of sleep and wake cycles. So our circadian rhythm repeats on each rotation of the earth, which is roughly 24 hours. So in daytime, melatonin secretion will be low while we are awake. And then as we are winding down for the night with the sun setting, our melatonin secretion will ramp up, which makes us feel sleepy, and then we go to bed. Melatonin was first isolated by Yale in 1958. Yeah, 1958. So like 60 years ago, only 60 years ago. Like we've been talking about the pineal gland since the 17th century, and we just recently figured it out. So it wasn't until the 70s that we figured out its role with our circadian rhythm, which is just mind-blowing to me, because that means that there's only more to learn. There's so much more that is, sorry about that, there's only so much more that is unknown, and that is honestly very humbling. I have endless fun facts about the pineal gland, but another one for you is that the pineal gland is a highly vascular structure despite its small size. The pineal gland is only second to the kidneys in terms of arterial supply, which I think is really intriguing. So the hormone melatonin has two important precursors, and that's the amino acid tryptophan and the neurotransmitter serotonin. So tryptophan can undergo a decarboxylation to form serotonin, and then within the pineal gland, serotonin is acetylated and then methylated to yield melatonin. You've probably heard of people taking over-the-counter supplements of melatonin to help them sleep. And while I can't give medical advice, I would proceed with caution because that can just be like a slippery slope. So because melatonin is a hormone, supplementing with it regularly has some potentially iffy consequences long term. So similar to how birth control pills shut down the production of those hormones in the brain, melatonin pills can have a similar effect. So if you're pumping yourself full of melatonin supplements every night, then the pineal gland will just be like, okay, great, look at all this melatonin. I don't need to make anymore. So it shuts down its own production, which I guess is technically fine, but whenever you decide to stop that supplementation, you're going to have much more difficulty falling asleep as the pineal gland readjusts and fires back up again. So it's up to you and your doctor to discuss if that's the right path, but remember that we just got started with this research in the 70s. So there's still a lot of unknown. Short-term use seems to be okay. Long-term use may be a call for concern, and I personally consider it to be a red flag. I often cite in favor with beginning with more holistic approach, like eating melatonin-rich foods before bed, like cherries or walnuts, and then progressing to further intervention if needed. There are so many tools in the toolbox for sleep, like tryptophan, magnesium, calcium, meditation, avoidance of caffeine and alcohol, proper timing of exercise, and a regulation of blue light, just to name a few. So blue light is actually the last thing that I want to touch on in reference to the pineal gland because it's so prevalent in our modern world. I'll keep it concise in that blue light blocks melatonin production and secretion. So the bottom line is that staring at all these screens, your phone, your computer, your TV, your iPad, your video games, staring at all these screens before bed can make you feel less drowsy and in turn make it take longer for you to fall asleep. If you don't believe me, just try it. Do it as like a personal challenge for yourself to not look at any screens for at least 2 hours before bed for a week. And I can almost guarantee that one, you'll likely struggle to do it because we all look at our phone before bed. And two, if you do it, you'll feel a difference. Maybe not after the first night or the second night, but as you commit to less screen time, I am confident in these physiological impacts on the system. If you don't want to be that extreme with it though, just be sure to at least turn down the brightness at night. We have blue light blocking glasses now that are a thing, so that's an option. It still doesn't have the same effect of just putting down the electronic devices, putting them away, picking up an actual book, or engaging in a real life conversation and connection with your partner, your family, your roommate, or whoever it is. Okay, so on to the thyroid gland. The thyroid gland is a butterfly-shaped gland located on the anterior aspect of the trachea, just inferior to the larynx. So just below the Adam's apple, essentially. And it has two lobes, or two butterfly wings, so to speak. And those lateral lobes are connected in the middle by the isthmus. Looking at the microscopic anatomy with our histology slide, we can see the thyroid gland is composed of hollow spherical follicles, and the walls of each follicle are formed by follicular cells, and then the central lumen is filled with a jelly-like substance called colloid. We can also see these parafollicular cells lying within the follicular epithelium, So the prefix para is a Greek derivative meaning at or to the side of. So we can think of parafollicular cells as the ones to the side of our follicles. So the thyroid produces two hormones, thyroid hormone and calcitonin. Let's start with thyroid hormone. This is the body's major metabolic hormone. So when we say thyroid hormone, the name actually applies to two similar molecules, and that is thyroxine, which we call T4, and then triiodothyronine, which is T3. And the difference between the two, between T3 and T4, is that T4 just has an extra iodine atom. So T4 has 4 bound iodine atoms, whereas T3 only has 3. Thyroid hormone affects virtually every cell in the body. So needless to say, that is pretty important. And though it is an amine, thyroid hormone is a special exception to our plasma membrane rules because we have specific transporters there that allow us to get thyroid hormone inside of the cell, where it can bind to the intracellular receptors within the cell's nucleus, where it initiates transcription for protein synthesis. So I've already mentioned it as a metabolic hormone, so we can see how that relates to our basal metabolic rate, our metabolism of carbohydrates, lipids, and proteins. It impacts our temperature regulation. So if someone has an excess of thyroid hormone, they'll typically have a very high activity level. They're typically very fidgety, they'll feel warm a lot, and they're often quite thin because their metabolism is like running like a racehorse. Whereas those who do not produce enough thyroid hormone often feel sluggish, cold, and tired. They'll often put on weight because their metabolism is moving like a snail. My fun fact for you about the thyroid gland is that the thyroid is the only endocrine gland that stores its hormones extracellularly in large quantities. So it stores enough thyroid hormone to last 2 to 3 months, which is pretty unique. The other hormone that the thyroid gland is responsible for is calcitonin, and this is released from the parafollicular cells. So thyroid hormone is released from the follicular cells, and then calcitonin is released from the parafollicular cells. Calcitonin's job is to lower blood calcium levels. So when blood calcium is high, the parafollicular cells will secrete calcitonin, and calcitonin lowers it by inhibiting osteoclast and by encouraging osteoblast. So to understand that, let's just refresh our memory of osteoclast versus osteoblast. Osteoblasts are bone building cells. So think of blast for building, and then osteoclast are bone crushing cells. Technically, it's not as dramatic as crushing. It's more like breaking down the bone. But for the sake of the memory tool, let's just think blast for bone building and then clast for bone crushing. So if we inhibit osteoclast, so if we stop the bone crushing, then we can keep the calcium in the bone by promoting our osteoblast, we can pull the calcium from the blood and deposit it into the bone, effectively decreasing our blood calcium levels. While we are on the topic of calcium, let's talk about the parathyroid gland. So the parathyroid glands are these very small glands located on the posterior aspect of the thyroid, and there are usually 4 parathyroid glands, 2 on each side like we see here, but the number can vary. As many as 8 parathyroid glands have been reported in some individuals, which is kind of neat. So parathyroid cells within the parathyroid gland secrete parathyroid hormone, or PTH. So PTH is the single most important hormone controlling our blood calcium balance, because precise control of these calcium levels is critical, because calcium homeostasis is essential for so many body functions, like the transmission of nerve impulses, for blood clotting. We know that we have to have it for muscle contraction. So maintaining a healthy balance or a healthy homeostatic range of blood calcium is very important to us. So the parathyroid hormone increases calcium levels in the blood by targeting 3 organs: the bone, the kidneys, and the intestine. So let's start with the bones. By stimulating osteoclasts, so remember bone crushing cells, we can break down some of that calcium-rich bony matrix so that it can be released into the blood, thus increasing our blood calcium levels. By way of the kidneys, we can enhance calcium reabsorption, or we can decrease calcium excretion, thus again effectively raising the amount of calcium in our blood. And then lastly, through the intestines, parathyroid hormone promotes the activation of vitamin D, thereby increasing the absorption of calcium through our diet. So we have to have vitamin D to be able to absorb calcium from our food. So by parathyroid hormone playing a role in vitamin D activation, we can achieve an increase in blood calcium in this way. So let's just make sure we clarify this. Parathyroid hormone and calcitonin have opposite effects. So they work as antagonists to one another. Parathyroid hormone is going to raise blood calcium levels, whereas calcitonin is going to lower it. My little tip as to how to go about remembering this, I think of calcitonin, I just think of like the first 2 letters, Ca, referring to the abbreviation for calcium, and I think of it as toning up the bone, like building up the bone. So with calcitonin, we have Ca, calcium, toning up the bone with calcitonin. And then, I don't know, you just have to remember that PTH is the opposite of that. I don't have a fun memory trick for that one. Okay, so the adrenal glands are these pyramid-shaped organs that sit on top of the kidneys. They are also sometimes referred to as the suprarenal glands. So the prefix supra meaning above, so above renal, suprarenal, above the kidneys. All the adrenal hormones help us cope with stressful circumstances in some way. So within the adrenal glands, we have 2 very distinct portions, the adrenal medulla and the adrenal cortex. The adrenal medulla is the innermost region, and it functions as part of the sympathetic nervous system. The cells here synthesize the catecholamines epinephrine and norepinephrine via a molecular sequence from tyrosine to dopamine to norepinephrine to epinephrine. There are a few exceptions, but in general, epinephrine and norepinephrine exert the same effects. So when a short-term stressor elevates the body to a fight or flight status, the sympathetic nervous system is called to action, and we will see the blood vessels constrict, the heart rate increases. Both of those things together will increase the blood pressure, blood glucose increases, so we have plenty available for immediate energy. The adrenal cortex, on the other hand, is the outer portion, and here we'll have the release of over 24 steroid hormones, collectively called corticosteroids. There are 3 different zones within the cortex, and each zone has a unique function, which you do need to know these zones with their unique function and hormones. So starting at the outermost, going inward, first we have the Zona Glomerulosa. And here we have the secretion of mineralocorticoids, the main one being aldosterone to help control the balance of mineral and water in the blood. The zona fasciculata is mainly responsible for glucocorticoids like cortisol. The innermost zone, so now we're deep in the cortex approaching the medulla, we have the zona reticularis. And here we'll see the gonatocorticoids being secreted. So these are the sex hormones, mostly weak androgens or male sex hormones, such as dihydroepiandrosterone or DHEA. And we can use these in the peripheral tissues to convert them to either testosterone or estrogen. And the exact role of the adrenal sex hormones is still in question, but we do know that they contribute to axillary and pubic hair formation. And in women, the adrenal androgens contribute to sex drive. And once a woman hits menopause, she'll be really thankful for these adrenal sex hormones because they largely account for the estrogen produced after menopause when the ovaries shut down that production. All right, last one, the pancreas. The pancreas is kind of neat in that it has both endocrine and exocrine functions. And if you don't know the difference between the two, all that means is that endocrine glands secrete their products directly into the bloodstream, whereas exocrine glands secrete their products into ducts that go directly onto the surface of wherever they're intended to go. So some examples of an exocrine gland would be like sebaceous glands that release oil to lubricate the skin or our hair, or sudoriferous glands, which is just a fancy way of saying sweat glands. So the pancreas's exocrine function is with the digestive system, and it'll secrete digestive enzymes to help break down food so we can absorb nutrients. That's not our focus today, though. We want to learn about its endocrine function and responsibilities, and we'll see its major role in the regulation of blood sugar levels. So if we look at the histology slide, we can see these little clusters. Let me get my mouse. Here's a little cluster right here. Here's another one over here. So we can see these little clusters called pancreatic islets, or the islets of Langerhans. And this is where we will have our two pancreatic hormones being produced. So within the islets, we have alpha cells that secrete the hormone glucagon, and then we have beta cells that secrete the hormone insulin. So glucagon is a hyperglycemic hormone. So it works to raise our blood glucose levels. It does this mainly by targeting the liver to break down glycogen to glucose. And it also tells the liver to synthesize glucose from lactic acid and from other non-carbohydrate molecules. So it's encouraging glycogenolysis and glyconeogenesis so we can ramp up the blood glucose. Insulin is the opposite. Insulin is a hypoglycemic hormone. And so its job is to lower the blood glucose. It also promotes the storage of fat, but that is a topic for later. So to lower the blood glucose, insulin will enhance the membrane transport of glucose. So we'll have the glucose being put into our cells, especially our muscle cells and our fat cells, so they can use this glucose as energy. So after the glucose enters the target cell, insulin binding triggers the oxidation of glucose for ATP production. It tells enzymes that it's time to build glycogen, and it'll convert glucose to fat. And it does so in this order. So as a general rule of thumb, the energy needs are met first. And then if we have extra left over, then we will make glycogen. And then if we have even more left over after that, the glucose will be converted to fat. So let's just summarize. So we have glucagon being released from alpha cells, and its job is to raise blood glucose. So as listed here on the slide, hypoglycemia is a main activator of its release. So hypoglycemia means that we have a low blood sugar. Hyperglycemia means that we have a high blood sugar. So when blood sugar is low, or we are hypoglycemic, that signals to glucagon like, hello, I need more glucose. And so we'll secrete glucagon and effectively raise the blood sugar. So just the flip-flop of that for insulin then, insulin works to lower our blood glucose. So if we are hyperglycemic or our blood sugar is high, then we will activate the release of insulin so we can bring the blood glucose back down. Okay, so let's talk about this in relation to diabetes. So, most of you, I'm assuming, are at least vaguely familiar with diabetes. So, we know that individuals with diabetes aren't able to regulate their blood glucose very well. So, they typically end up with persistent hyperglycemia or an abnormally high blood sugar level. Think of insulin as the key that unlocks the doors to your cell to allow glucose to enter. So every time you eat a meal, insulin is released by your pancreas to help shuttle the glucose into your cells. So without insulin, your cells cannot accept glucose. As a result, the glucose builds up in your blood. Over time, this extra sugar can be damaging to the blood vessels throughout the body. And that's why diabetes can lead to blindness, kidney failure, heart attacks, and stroke. High blood sugar can also damage your nerves by creating a condition known as neuropathy that causes numbness, tingling, and pain. Because the damage to their blood vessels and nerves, diabetics may also suffer from poor circulation and a lack of feeling in their legs and feet, which can lead to poorly healing injuries that can in turn end as amputations. Diabetes also have a significantly increased risk for dementia as Alzheimer's is developing a new catchy term, sometimes referred to now as type 3 diabetes, but that's a conversation for a different day. So technically, there are two main types of diabetes, type 1 and type 2, and they are dramatically different from one another. Just as a side note, there's technically another type. It's called gestational diabetes that can occur during pregnancy, but we aren't going to get into that in this class. In this class, let's focus on type 1 and type 2. So type 1 diabetes is an autoimmune disorder, and the immune system of someone with type 1 diabetes mistakenly destroys their beta cells. Which hormone is synthesized by the beta cells? Insulin, right? So without insulin, their blood sugar just goes up and up and up to unsafe levels. Type 1 diabetes is therefore treated with injections of insulin, a type of hormone replacement therapy to make up for that lack of production. Type 1 diabetes was previously referred to as adolescent onset diabetes because this autoimmunity often develops in childhood. This is a very small proportion of the diabetic population. So only about 5% of individuals with diabetes have type 1. The remaining 95% of the diabetic population has type 2 diabetes, which has a very different developmental pathology. So type 2 diabetes is often resulting from something that we call insulin resistance. And it has strong ties to our diet and lifestyle, so what we eat and how we exercise. So with type 2 diabetes, the beta cells are fine. Insulin is present, but its effects are insufficient. The body has become resistant to insulin, so it doesn't work the way that it used to. So what happens is when you continually bombard your body with carbohydrate-rich foods and foods high in saturated fats, so like breads, pastas, refined processed food items like chips, French fries, sugary things like soda, sweets, things like that, insulin is going to go sky high so that your body can process that rapid intake of calories. And if you do this time and time again, this just becomes your way of life, that's just your normal diet, then the pancreas is working overtime all the time, constantly pumping out insulin. Well, insulin loses its effect, and over time, the pancreas might not be able to keep up. So in a clinical setting, more often than not, you'll see the use of pharmaceuticals like metformin being used as a treatment. And I mean, it works in the sense that metformin controls the blood sugar levels, but it's not addressing the cause of the imbalance in the first place. So it's basically like a Band-Aid over the wound, the mentality of like, if I can't see it, then it's not there. and that's clearly not the case. Metformin is proven to be less effective than lifestyle changes, and it has a whole laundry list of potential side effects and interactions. But swallowing a pill is much easier than changing your entire lifestyle. And that's sad to say, but it's also sadly true. The bad news is that diabetes is the seventh leading cause of death in the United States. But the good news is that type 2 diabetes is almost always preventable, often treatable, and sometimes even reversible through diet and lifestyle changes. So if you take nothing else from my class, I hope that I can share even a small piece of my energy and excitement about taking intentional care of our bodies and using these physiological mechanisms to understand how disease develops in the body, and then also the appropriate steps towards prevention and treatment.